Our interest in fitting a multiple linear regression model could alternatively be to identify important predictors of an outcome or predicting the continuous response. When interest lies in modeling a continuous outcome y given p predictor variables measured for n samples, forward stepwise, backward stepwise, and best subset methods are commonly used to obtain a parsimonious model. One problem is that we may want to build a multiple linear regression model using gene expression data, which cannot be estimated if the number of covariates p is greater than the sample size n. In fact, most statistical modeling methods, including multiple linear regression, require that the number of predictors p be far less than the sample size n. For data sets where the number of covariates p exceeds the sample size n, the backward stepwise procedure cannot be undertaken. When p is large, the best subset procedure is computationally prohibitive. Moreover, beta sub j's estimated using these model selection procedures can exhibit extremely large variances when covariates are collinear. Penalized or regularization methods such as ridge regression, least absolute shrinkage and selection operator, or LASSO, and elastic net are alternatives to traditional statistical models that can be used to estimate a regression model when p is greater than n. Penalized models provide penalized estimates for all covariates and thus trade unbiasedness for smaller variance and improve prediction accuracy. For certain types of penalized models, such as the LASSO and elastic net, coefficients associated with very small effects are shrunk to zero, and thus variable selection is part of the fitting procedure. Solutions based on penalizing the size of the beta sub j estimates so that the bias introduced is traded for reduced variance of the estimates have been proposed. A specific method called ridge regression can be expressed using this equation. Here, lambda is the tuning parameter that controls the amount of shrinkage. If lambda equals 0, the solution is the ordinary least squares estimate. As lambda increases, the amount of shrinkage of the parameter estimates increases. The ridge estimates differ depending upon the scaling of the covariates used, so typically, covariates are standardized prior to model fitting. Referring to the model equation, note that beta naught is not included in the penalty term, as penalizing the intercept would make the procedure dependent on the origin chosen for y. For centered inputs, we estimate beta naught using this equation, and the remaining coefficients can be estimated using ridge regression without the intercept. Also note that the solution depends on the value of lambda. This prostate cancer dataset will be used to illustrate fitting penalized models including ridge regression. The outcome is log prostate-specific antigen, and predictor variables include log cancer volume, log prostate weight, age, log of benign prostatic hyperplasia, seminal vesicle invasion, log of capsular penetration, Gleason grade, and percent of Gleason scores of 4 and 5. The train variable is a logical variable, or true-false, and designates whether a subject should be included in model building, if so train equals true, or testing, and if testing, train equals false. Before estimating ridge regression, let's first standardize the predictor variables. Now we can fit our multiple linear regression model where log of prostate-specific antigen is modeled by all other variables for the subject for which train is equal to true. We can see our coefficient estimates are all non-zero, and we can predict log prostate-specific antigen using the subjects for whom train does not equal true, as those subjects are our independent test set. So that you can see how the ordinary least squares is related to ridge regression, we could have equivalently used the matrix calculation to obtain our ordinary least squares estimates. Here is the code where we want to extract the X matrix for the subjects for whom train is equal to true, and extract the Y response vector for the subjects for whom train is equal to true. And then we can perform the matrix calculation to estimate our coefficients. These estimates are equivalent to those from the previous slide, which were obtained using the LM function. The ridge estimates are obtained using this matrix calculation, where lambda is our penalty parameter and I is a diagonal matrix with 1 along the diagonal and zeros as all off-diagonal elements. Here is the code that performs this matrix calculation to estimate our ridge coefficients, where 24.2 was arbitrarily used as the value for our penalty parameter lambda. The intercept is simply the mean of the response. When comparing these ridge coefficient estimates to those from the ordinary least squares, you should notice that these coefficients have been shrunken towards 0. We can predict log prostate-specific antigen using the subjects for whom train does not equal true, that is our test set. Having chosen a final model, we need to estimate its prediction error. For multiple linear regression, prediction error is typically measured by the mean squared error and serves as a summary measure indicating how well a model predicts the response for a future observation. Because statistical models either directly or indirectly attempt to minimize some quantity of interest, when examining the prediction error using the same data that were used in constructing the model, we will have an overly optimistic picture of the accuracy of our model. Therefore, it is preferable to use an independent test set when evaluating model performance. Comparing the ordinary least squares and ridge coefficient estimates using predicted mean squared error for the test set subjects, the biased ridge estimates have lower mean squared error, indicating ridge outperforms ordinary least squares for prediction. That comparison, of course, was made for a fixed value of lambda. The question you may have is, how do you select an appropriate value for lambda? Typically, we define a sequence of possible lambda values, fit the ridge regression for each lambda, then compare the performance using some quantity, such as predicted mean squared error on a test set, and take the lambda attaining the minimum value. This code develops a vector lambda, which is a vector of length 200 that sequences from 0 to 120, then sets up a vector storage location for mean squared error and a matrix to store the ridge coefficient estimates. Then for each value of lambda, we use our matrix calculation to obtain our ridge coefficient estimates, predict log prostate-specific antigen using those coefficients, then calculate the mean squared error. After 200 ridge regression models are fit, we see which has the smallest mean squared error, so for this data set and sequence of lambdas, we would select lambda to be 13.26. These plots may help to understand ridge regression. On the left is a graph of mean squared error plotted by lambda. We can see that mean squared error decreased until around 13 and then increases. So our best fitting model corresponds to the point. On the right is a trace plot of our ridge coefficient estimates, where the coefficient estimates for each variable is plotted against lambda. Note, when lambda equals 0, we have our ordinary least squares estimates. As lambda gets larger, the ridge coefficient estimates are shrunken. Notice, though, that the ridge estimates do not converge to 0, but rather are some shrunken non-zero value, even for very large lambda penalty values. Ridge coefficient estimates, though biased, have smaller variance and tend to have improved performance, that is, lower test set error, when compared to ordinary least squares estimates. However, the ridge solution does not provide a parsimonious model because all p predictors will have a non-zero coefficient estimate. For gene expression microarray data, or high-throughput genomic data sets, this makes the final model lack interpretability. The least absolute shrinkage and selection operator, or LASSO, imposes a constraint similar to ridge regression, given by this equation, where now the penalty is based on a multiplicative factor times the sum of the absolute values of the coefficient estimates. So it is also referred to as an L1 penalty, or is called an L1 penalized model. Again, lambda is the tuning parameter that controls the amount of shrinkage. As lambda increases, the amount of shrinkage of the parameter estimates increase. Additionally, because L1 penalty shrinks some coefficients to be exactly 0, it is better than ridge regression in terms of model parsimony and interpretability. The GLM-net R package is commonly used to fit LASSO models. The GLM-net function automatically fits a LASSO model for several values of lambda and allows the user to select a model using their own criterion. In this example, the GLM-net function is used where the predictors x are in x train, the response y is in y train. We are fitting a LASSO penalized linear regression model, so the family is Gaussian. There were 71 different lambda values generated, and thus 71 LASSO models fit. We predict the response for each value of lambda using our X-test object, which results in a matrix with subjects in rows and lambdas in columns. To calculate the prediction mean squared error, we create a matrix that stores each test set subject's LPSA in a row, which is repeated to match the length of lambda. Then we calculate mean squared error and find which has a minimum value and use that to extract the coefficients for our best model. For the LASSO, 5 variables have shrunken non-zero coefficient estimates, while 3 variables' coefficients have been shrunken to be identically equal to 0 and thus are not included in the model. So the LASSO solution can perform automatic variable selection. A generalized expression for penalized models is given by this equation for q greater than or equal to 0. For the LASSO model, q equals 1. For ridge regression, q equals 2. Values of q in between 1 and 2 provide a compromise between the LASSO and ridge regression. However, users should note that when q is greater than 1, coefficients are no longer set exactly equal to 0. Therefore, the elastic net penalty was introduced to maintain the benefits from both ridge and LASSO and is given by this equation, where alpha weights the amount of the penalty placed on the ridge and the LASSO components. Be sure not to confuse alpha here with the type 1 error level we used in hypothesis testing. The GLM-net function includes alpha equal 1 as a default, so by default GLM-net fits a LASSO model. We could change alpha equal to 0 to fit a ridge model. Let's now look at an elastic net model where alpha equals 0.5, which balances the LASSO and the ridge. Again, we use the GLM-net function where the predictors x are in x train, the response y is in y train, the family is Gaussian, and we are fitting an elastic net model with alpha equals 0.5. There were 73 different lambda values generated, and thus 73 elastic net models fit. We predict the response for each value of lambda using our X-test object, which results in a matrix with subjects in rows and lambdas in columns. To calculate the prediction mean squared error, we create a matrix that stores each test subject's LPSA in a row, which is then repeated to match the length of lambda. We then calculate mean squared error and find which has a minimum and use that to extract the coefficients for our best model. For the elastic net with alpha equals 0.5, 6 variables have shrunken non-zero coefficient estimates, while 2 variables' coefficients have been shrunken to 0 and thus are not included in the model.